Hello everyone. Today we have a very interesting lecture. It's straight out of science fiction. So we'll talk about quantum teleportation. But before we get there, we have to say something about quantum circuits. Okay, so let's see. Remember, last time we talked about 1 qubit gates. So 1 qubit gate we think of as, we have a wire that carries a qubit of information. So let's say alpha 0, 0 plus alpha 1, 1. And now we have a gate which acts on it. And remember, what a gate does is it takes this two-dimensional complex vector space. The state is a unit vector in that space, and then we take the space and we rotate it. Okay, this rotation in the complex vector space is called the unitary transformation U, which in this case is a 2 by 2 unitary transformation. So U is 2 by 2 unitary transformation. And the fact that it's unitary is given by the condition U times U dagger is U dagger times U is the identity. So we saw several examples of such gates, and they included X, the NOT gate, Z, the phase flip, H, the Hadamard gate. Okay, so what these do is they take the input qubit and convert it into some new qubit, alpha 0 prime 0 plus alpha 1 prime 1. Now, of course, you remember that you could prescribe the this rotation, the unitary rotation, by either specifying the unitary matrix, or you could just say 0 gets mapped to what and 1 gets mapped to what. Right? So if you specify these 4 numbers, which are that 0 gets mapped to A0 plus B1, and 1 gets mapped to C0 plus D1, then you specified what the mapping is, because it's a linear map. So now if you have alpha 0 plus beta 1, what does it go to? Well, it goes to alpha times A0 plus B1 plus beta times C0 plus D1. Also, the unitary matrix that describes how these, the mapping is just given by A, B, C, D. Okay, so that's what we did last time. And now, this time we are going to talk about 2 qubit gates. So here's our picture. So we have 2 wires that are coming in, each carrying a qubit. And then this encounters a gate U, and then you have 2 wires coming out which are now carrying 2 qubits which are in a different state. So what's the state of our initial qubits? Well, remember that the state of 2 qubits is described by 4 complex numbers, the 4 complex amplitudes, alpha 0, 0 through alpha 1, 1. And the output qubits are described by 4 new complex numbers, alpha 0, 0 prime through alpha 1, 1 prime. So now, the way that this output state is related to the input state is, of course, given by this unitary transformation U, which is a linear transformation. It's what's the dimension of this transformation? Well, clearly U is 4-dimensional. Right? Meaning, if you write it out, it would look like this kind of matrix. Okay. And of course, U satisfies this condition. U dagger equal to U dagger U. It's the identity. And once again, you can specify the action of U by just saying, how does it map 0, 0? How does it map 0, 1? etc. How does it map 1, 1? So if you say, how does it map each of these 4 states, then you have specified U as well. Okay, so let's say that it maps 0, 0 to A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. Then we know that the first column of this matrix is going to be A, B, C, D. Right? So check that you understand why this is. Right? Because 0, 0 is this vector. Okay, so if you want to know what does U map 0, 0 to, you multiply this matrix U by this vector. And what do you get? You get this column, A, B, C, D, which is exactly what this was. Okay, so make sure you understand all this. Okay, so now let's look at an example of a 2-qubit gate. This is the most basic of the 2-qubit gates. So it takes as input 2 qubits, outputs 2 qubits, and it's denoted by this funny symbol where there's a dot on the one side, a line which with this circle around, which denotes an XOR. Okay, so if this was a classical gate, so if the inputs A and B were classical, then the outputs would look like this. The first input is let through unchanged, and the second bit, so the first bit is let through unchanged, and the second bit is flipped if and only if the first bit is 1. Okay, so the first bit, this is called the control, and that bit is called the target bit. Okay, so the CNOT stands for control NOT. All right. Okay, so now remember what the rules were, that if you want to describe what the CNOT gate is, it's sufficient to describe what it does on input 0, 0, 0, 1, 1, 0, 1, 1. So let's see. How does the CNOT gate map 0, 0? So now the control bit is 0, so the target bit remains unchanged, so it gets mapped to 0, 0. How about 0, 1? Well, the control bit is still 0, so the target bit is unchanged, so 0, 1. How about 1, 0? Well, now the control bit is a 1, so the target bit flips, and so it gets mapped to 1, 1. How about 1, 1, 1? Okay, so this time, okay, again the control bit is 1, so the target bit flips. So the output is 1, 0. So now you know exactly how CNOT works, because if you're given any superposition of these 4 states, so if you have alpha 0, 0, okay, so if you had this superposition alpha 0, 0, 0, 0 plus alpha 0, 1, 0, 1 plus alpha 1, 0, 1, 0 plus alpha 1, 1, 1, 1. So what does it get mapped to under CNOT? Well, the answer is simple. What it does is 0, 0 stays unchanged, so it goes to alpha 0, 0, 0, 0. 0, 1 unchanged, so 0, 1, 0, 1. Now, 1, 1 gets mapped to 1, 0, so you'd have alpha 1, 1, 1, 0. And 1, 0 gets mapped to 1, 1, so you get alpha 1, 0, 1, 1. Okay, we can also write out what the matrix is corresponding to CNOT. And CNOT is given by this matrix. So make sure you see why this matrix is giving you this transformation. right? Because this one gives you the first column, which is 1, 0, 0, 0. This gives you the second column. This gives you the third column, where you get a 1 in the last entry because you have a 1, 1. This gives you the fourth column where you have a 1 in the third entry. And of course, it's unitary. To check that, you just check that CNOT times CNOT conjugate transpose is the identity. In fact, again, what you have is that the conjugate transpose is itself, and so CNOT is its own inverse. If you apply it twice, you get back to where you started from.